Every year, over 420,000 people experience sudden cardiac arrest. Cardiac arrest differs from a heart attack where a blockage prevents blood flow. The American Heart Association defines a cardiac arrest as an abrupt loss of heart function and happens when the heart's electrical system malfunctions and stops beating properly. This is often fatal if appropriate steps are not taken immediately, such as fast response rates from the first responders and quality CPR, thus a 10% survival rate, and this is why good CPR is essential. The AHA guideline states appropriate CPR having chest compression depth of 2 to 2.4 inches. This can be done either manually or mechanically. In order to test and validate the mechanical CPR devices, a model that represents the human thorax is a necessity. The current model DefibTech uses consists of a spring system of 30 to 60 pound force per inch that only accounts for the elastic property of the chest. There is no damping that causes the viscous property of the human body, which is typically 200 to 400 newton seconds per meter. So our objective of the project was to create a model that will allow for benchtop testing of this mechanical CPR devices and to be able to see how human-like the model is by applying forces and comparing the chest versus displacement of actual human values.
This is our small-scale prototype of the device. It consists of a pneumatic spring damper system with a contact plate on top and a motor that sits in the base. The spring acts as the elastic part of the chest during compression, much like current CPR mannequins. During decompression, the pull damper creates the viscous properties of the chest. There are aluminum alignment rods which prevent the contact plate from tilting when compressed. A stepper motor will be used to control the valve on the dashpot, which affects the amount of airflow, changing the damping that is applied to the device. As seen in the video, when the prototype is compressed, only the spring reacts. This is because the pull damper allows for air to easily flow out of the valve. In decompression, however, the spring is pushing up on the contact plate while the pull damper only allows a specific amount of air in, dissipating the energy of the system and creating the desired hysteresis. Other important components of our design is an accelerometer, which is used to determine the forces applied to the device during recoil. A load cell is also going to be implemented to measure directly the applied external force during compression. Initially, a time-of-flight sensor was used to determine the displacement of the compression, which is important because compressions have to reach a depth of at least 2 inches for quality CPR. But the time-of-flight sensor had a large amount of noise, so an ultrasonic sensor is being used instead, which has a lot less variation. The data collection from these sensors and the motor control is done with a Raspberry Pi 3B+. This was chosen because it has a faster processing speed and can be a standalone computer.
Some results from initial testing of our small-scale prototype are highlighted on this slide. The purpose of this testing was to see the damping effects of the spring and dashpot in the system. These results may change based on differing the spring or valve constants. In this case, the valve constant was initially unknown. To obtain these results, the openness of the dashpot valve was varied between open, half open, or closed. The top plate of the thorax model was compressed approximately 1 inch, and then the force holding the plate down was released. An ultrasonic sensor collected position data for the top plate. On the left are two graphs showing raw position in centimeters versus time in milliseconds data in Excel. The top graph shows the position of the top plate when the dashpot valve was open. In this case, the top plate returned to its initial position almost immediately. It did oscillate at the top, but that was due to the natural spring behavior. The bottom graph shows the position of the top plate when the dashpot valve is closed. It took much longer to get back to this initial position. It also occurred in a nonlinear fashion, which was desired. Once this raw data was collected, it was processed using a MATLAB simulator as seen in the figures on the right. The point was to determine the unknown valve constant of the dashpot. However, since this isn't the valve that will be used in the final prototype, the specific values aren't displayed. But it can be seen that the experimental data agrees with the simulation using the estimated valve parameter. Therefore, this can be used to design the final prototype.
For the future work of this project, we hope to finalize the large-scale product as seen in the SolidWorks model here. We have decided to remove the alignment rods and use only springs, totaling in 5 smaller size springs to be used around the radius of the device to create better stability as the rods were creating too much friction. Next, we want to decide on a material to fabricate the device out of, either professional level 3D printing using something like fiberglass or anything better than PLA, or producing it out of high quality metal like steel in a machine shop. We would also like to incorporate new features into the device, such as a load cell that would be able to record compression forces during motion, as well as a motor that would be used to open and close the valve of the dashpot more precisely than by hand. We would also like to develop a data analysis tool that would automatically format the data collected by the Raspberry Pi and output relevant information in the form of graphs and charts, for example, a force displacement graph that is updated as the machine is in use. Lastly, once the final build is assembled, we would need to include a full-size dashpot and run some tests to calibrate the final product.